Have you ever wondered how scientists know exactly where to place an element like sodium or chlorine on the periodic table? It all boils down to one fundamental concept: electronic configuration. When we talk about an element's position in the periodic table, we are actually talking about its electrons, especially the ones in the outermost shell. These electrons dictate everything from reactivity to bonding preferences. Now, to figure out how electrons are distributed, we use quantum numbers and a rule called the Aufbau principle, which tells us the order in which orbitals are filled. The arrangement of elements in the modern periodic table isn't just alphabetical or historical, it's based on increasing atomic number and electronic configuration. Each horizontal row, called a period, corresponds to the principal quantum number, that is, the outermost shell being filled. The vertical columns, or groups, contain elements with similar valence shell configurations, which is why fluorine and chlorine behave so much alike in reactions. Essentially, the periodic table is a beautifully organized grid that mirrors the electron-building process inside atoms. Let's now dive deeper into how electronic configurations vary across periods. A period in the periodic table signifies a new energy level being occupied by electrons, and this starts with the lowest one, n equals 1. For example, hydrogen has the configuration 1s1 and helium has 1s2 that completes the first shell, and hence, period 1 has just 2 elements. When we step into the second period, lithium begins the filling of the 2s orbital, and as we move right, we fill the 2p orbitals, finishing with neon at 2s2 to p6. This gives us 8 elements in period 2. The third period sees electrons entering 3s and 3p orbitals, again 8 elements. But things get more interesting in period 4. After filling 4s orbitals, electrons start occupying 3d orbitals. That's where transition metals begin. So, from scandium to zinc, we fill the 3d series, and finally, the 4p orbitals are filled by krypton. The pattern continues into longer periods like period 6 and 7, which include f-block elements. These variations explain why periods have different numbers of elements. It's all about how many orbitals are available at each energy level. Here's something fascinating. The number of elements in a period is not random. It's actually twice the number of orbitals available in that energy level. For example, when n equals 5, orbitals like 5s, 4d, and 5p are being filled. That gives us 9 orbitals, and since each orbital holds 2 electrons, we get 18 elements in the fifth period. As we reach the sixth period, things expand further. We fill 6s, 4f, 5d, and 6p orbitals, accommodating up to 32 elements. The inner transition elements, the lanthanoids and actinoids, belong here, but to avoid stretching the table sideways, they are placed separately at the bottom. You'll often see a visual, an Aufbau chart, that lays out this electron filling sequence, guiding you from 1s to 7p. This layout is not just for convenience, it reflects real energetic preferences of electrons. These detailed arrangements help explain why certain elements like cerium start filling the 4f orbitals, forming the f block, and why the seventh period, although incomplete, mirrors the sixth in complexity. Now, let's explore the vertical structure, the groups. If you pick any column, say group 1, you'll find all the elements have 1 electron in their outermost s orbital, written as an s1. That includes lithium, sodium, potassium, and so on. Because they all share this valence configuration, their chemical behavior is remarkably similar. They're all soft metals, react violently with water, and form strong bases like sodium hydroxide. On the other hand, noble gases have a filled outer shell, typically Ns2, Np6, making them stable and unreactive. So, We can say that the properties of elements in a group repeat periodically because their valence shell structures are the same. This idea of grouping based on electron configuration is why elements in a group tend to form ions of the same charge, participate in similar reactions, and often have predictable compounds. Simply put, the periodic table is a roadmap of recurring electronic patterns. Let's break the table down further into blocks, and no, not Lego blocks, we mean electron blocks. The periodic table is neatly divided into S, P, D, and F blocks based on the last subshell receiving an electron. The S block contains groups 1 and 2. Their outer configurations are NS1 and NS2, respectively. These are the reactive metals like lithium, sodium, and calcium. The P block spans groups 13 to 18, with outer shells ranging from NS2, NP1 to NS2, NP6. This block is home to nonmetals, metalloids, and noble gases, chemically diverse but structurally similar in electron terms. The D block includes transition elements like iron and copper. Their outer configurations involve N-1d orbitals being filled. These elements often form colorful compounds and multiple oxidation states. Finally, we have the F block, the lanthanoids and actinoids, where the F orbitals are filled. A quick visual cue. Check out figure 3.3 in your textbook. It color codes the periodic table by blocks and even shows which elements are metals, nonmetals, and metalloids. This blockwise understanding helps predict trends like magnetism, conductivity, and reactivity. Two elements in the periodic table break the mold: hydrogen and helium. Let's start with hydrogen. It has a 1s1 configuration, just like alkali metals. It can lose one electron to form a hydrogen ion, H+. But it can also gain one electron to resemble halogens like fluorine and form H-. That's why hydrogen is placed separately at the top, because it behaves like a chameleon. Helium, on the other hand, has a configuration of 1s2, which suggests it should be in the S block. But because its shell is completely filled, helium behaves like a noble gas, inert, unreactive, and stable, so it's placed in group 18. These special placements remind us that periodic classification is not just about counting electrons, but also understanding how elements behave in real chemical environments. Exceptions like these bring depth to the periodic table and show that chemistry, while systematic, always has room for nuance. Let's quickly recap what we've learned about electronic configurations and their relationship with the periodic table. First, we saw that each element's position in the periodic table is directly linked to its electronic configuration. Periods reflect the principal quantum number, the shell being filled, while groups indicate similarities in valence shell electrons. We understood that different blocks, S, P, D, and F, correspond to different types of subshells being filled. As we progress across periods, electrons fill orbitals in a specific order, shaping the structure of the periodic table. Vertical columns, or groups, bring together elements with similar chemical properties due to their shared valence shell structure. Special cases like hydrogen and helium remind us of chemistry's complexity and flexibility. In essence, the periodic table is not just a chart, it's a living document of electron behavior and atomic architecture. I hope this session helped you appreciate how deeply electronic configurations govern the logic of the periodic table, from classroom examples to the atomic design of real-world materials. Stay curious, and I'll see you in the next lesson where we'll explore more of the periodic wonders of chemistry.